Wireless electrical power in space, applications, technologies, and prospects. Wireless electrical power transfer, WPT, has the potential to revolutionize space exploration and operations. This technology can overcome many limitations of traditional power systems, such as reliance on physical connectors or solar panels, making it a critical innovation for future space missions. Below is a comprehensive overview of its applications, technologies, current status, and future prospects. Applications of wireless power in space. Powering satellites and spacecraft. Dynamic power sharing. Wireless systems can enable satellites to transfer power among themselves in constellations, ensuring consistent functionality even during orbital shadow periods. Supplement to solar panels. In deep space missions or regions with limited sunlight, wireless power transfer can act as an alternative energy source. Lunar and planetary exploration. Rovers and landers. Rovers operating on planetary surfaces like the Moon or Mars can receive power wirelessly from stationary landers or orbiting platforms, removing the need for large onboard batteries. Lunar bases. A central power station on the Moon could distribute energy wirelessly to habitats, mining equipment, and scientific instruments. Orbital construction and maintenance. Space station assembly. Wireless power eliminates the complexity and risks of using wired systems in zero-gravity environments during the construction of space habitats or orbital stations. Power for drones. Maintenance robots or drones in space can be powered wirelessly, extending their operational time and range. Beamed energy for propulsion. Solar sails. Beaming energy to solar sails can provide propulsion, enabling spacecraft to traverse interstellar distances without fuel. Onboard propulsion systems. High-power beams from Earth or orbit can power ion thrusters for deep space missions. Space debris management. Satellites involved in debris removal can recharge wirelessly from orbital power stations or other satellites, reducing their reliance on bulky batteries. Reducing wear and tear. The absence of moving parts in wireless systems reduces wear and tear compared to mechanical connectors, making them more reliable in harsh space environments. Wireless power transfer technologies. Microwave power transmission, MPT. Description: uses microwave frequencies, typically 2.4 GHz to 5.8 GHz, to transmit power wirelessly. Receivers, rectennas, convert microwaves into electricity. Advantages: high efficiency over long distances and scalability. Applications: power beaming from orbital platforms to planetary surfaces or inter-satellite power sharing. Laser-based power transmission. Description: lasers transmit concentrated light beams to photovoltaic receivers, which convert light into electricity. Advantages: precise targeting and minimal energy dispersion over long distances. Applications: powering rovers, satellites, or space habitats where precision and high power are required. Inductive and resonant coupling. Description: transfers power through magnetic fields over short distances, typically within a few meters. Advantages: efficient for intra-vehicle or intra-module power distribution. Applications: powering internal systems of spacecraft or tools used during construction. Hybrid systems. Description: combines multiple technologies, such as MPT for long-distance power transfer and inductive coupling for local distribution. Advantages: versatility and adaptability to various space missions. Current status of wireless power in space. Technological demonstrations. Space solar power experiments. Agencies like NASA and JAXA have tested wireless power transmission for space-based solar power (SBSP) systems, aiming to beam solar energy collected in space back to Earth. R&D projects. Private companies, e.g., SpaceX, Northrop Grumman, and research institutions are exploring applications of MPT and laser power systems. Successful experiments. Microwave beaming. In 2020, the Naval Research Laboratory conducted a successful experiment aboard the X-37B spaceplane, demonstrating microwave power transmission in space. Laser beaming. Experiments on Earth have achieved high-efficiency power transmission over distances of several kilometers, paving the way for space applications. Challenges. Energy losses. Wireless power systems still face significant efficiency losses, especially over long distances. Safety concerns. High-powered microwave or laser beams must be carefully managed to avoid damage to sensitive equipment or harm to astronauts. Alignment and targeting. Maintaining precise alignment between transmitters and receivers in dynamic space environments remains a technical challenge. Prospects and timeline. Short term, 2024 to 2030. Lunar exploration. Wireless power systems may be deployed for powering rovers and instruments on the Moon under programs like NASA's Artemis and ESA's Lunar Gateway. Satellite power sharing. Demonstrations of inter-satellite power transfer are likely, aiding large satellite constellations like Starlink. Space-based solar power, SBSP, pilots. Small-scale SBSP systems with microwave or laser transmission may be tested in low Earth orbit, LEO. Medium term, 2030 to 2040. Lunar and Martian bases. Fully operational wireless power grids may support human habitats, mining operations, and vehicles on the Moon and Mars. Beamed propulsion. Early versions of propulsion systems powered by microwave or laser beams could become operational, enabling faster interplanetary travel. Orbital factories. Wireless power systems may energize orbital manufacturing facilities and large-scale construction projects. Long-term, 2040 and beyond. Interstellar missions. Advanced solar sails and other propulsion systems powered by wireless energy beams could enable missions to other star systems. Global space-based power grids. Large-scale SBSP systems could provide clean energy to Earth while also powering space infrastructure. Permanent space habitats. Wireless power will play a critical role in sustaining self-sufficient space colonies. Wireless power transfer is poised to transform space exploration and settlement by offering flexible, efficient, and scalable energy solutions. Although technological and operational challenges remain, ongoing research and advancements are likely to address these hurdles in the coming decades. As nations and private entities push the boundaries of space exploration, WPT will be a cornerstone technology for powering the next generation of space missions.